Okay, welcome everyone. I am Ansar, your helping hand, and today we are going to be proving that the sampling distribution of the sample variance is related to the chi-squared distribution. Specifically, we're going to be proving that when you take the sampling variance or the sample variance and you multiply it by n-1 and then you divide by sigma squared, that has a distribution of chi-squared minus 1. So that's what we're proving. That's what we're proving over there. Okay, so this proof video is going to be a bit different, and the reason for that is because it is an incredibly long proof. Well, I mean, it's not incredibly long, it's just it has a lot of different parts that you need, so the prereqs are a bit more intense than our previous prereqs. So I'm kind of going to go over the setup, I'm going to go over the prereqs. I'm not going to prove the prereqs, but I will leave a PDF in the description below that has the PDF of all the proofs, and in that PDF of all the proofs of the prereqs are done. Okay, so this is our setup, right? We have a sample, right? A normal distribution or a normally distributed sample. So we have n sample points, or n sample, our sample size is n, and these sample points all have a normal distribution that is got a mean of mu and a variance of sigma squared. Okay, so then we define what our sample mean is. So our sample mean is xn bar. And we've talked about this multiple times, but it's just 1 over n, and you sum up all of your xi's. And then you have your sample variance. You'll see I don't put an n over here, and the reason for that is it's just going to make this whole proof a lot longer. If I have to keep on putting n's everywhere I put an s, you just kind of know that S has a sample size, and that sample size is n, basically. So that's our setup, and if we have those three facts, then the following statements are implied by those facts. So the first implication is that xn bar and s squared, or our sample variance, so our sample mean and our sample variance, that those two things are independent. The proof of this is out of the scope of the whole module, and yeah, you don't really need to know it. It's just, it is a fact. If you are interested in why this is true, if you're interested in why this is true, you can go and look at something called, I hope I'm spelling this correctly, Cochrane's theorem, which kind of gives you a result that implies this. Okay, and then the second implication, which is the more important implication, is that if you have this setup over here, that if you take your sample variance and multiply it by n-1 and divide by sigma squared, that is a chi-squared distribution with n-1 degrees of freedom. Okay, so in order to begin the proof, there's like 4 sub-proofs that need to be done. They're not necessarily they need to be done, it's just they're prerequisites in terms of during the proof, we do a manipulation, and the manipulation requires us to know why the manipulation requires some justification, and these prerequisites are those justifications, basically. And I'm not going to prove them in this video, but I will have the PDF that has, I will link to the PDF that has the proofs for each of these things. I will kind of explain them, but yeah. So the first fact that we need, okay, I'm just using 2 fingers. Okay, so the first fact we need is this one over here. So this fact just says that when we take all of our observations and we subtract the mean from them and we take the sum of all of those deviations, basically, this can be thought of as a deviation or a form of deviation. When we take all of those, they will be equal to 0. And essentially the way you prove this is, well, I mean, I'm not going to prove it, but if you think about what xn bar is equal to, xn bar is equal to basically 1 over n multiplied by the sum, and then if you want to just get the sum, you would basically multiply by n, and then there's a whole thing that essentially you're just multiplying by n. Yeah, it's not a difficult proof. You just basically have to write out, sorry, I'm kind of can't really explain it out of my mouth. I have to write it down, but basically if you write out this thing in full, you'll see that it is actually equal to 0, and I do it in the PDF, so you can look at the PDF. The second fact we need is this fact over here, which seems like a little interesting thing, but basically what it's saying is that if we take all of our observations and we subtract our sample mean, and then square that and divide by our population variance, that's equivalent to taking our sample variance, multiplying by n minus 1 and dividing by our population variance. And this proof is also quite simple. You just have to look at what the definition of s squared is. S squared is 1 over this thing over here, well, this sum over here. So if you multiply n minus 1, you're left with this particular sum, and then it's just, yeah, straightforward from there. The second fact that we need is we need this fact over here, which is if you take the sample mean and you subtract the population mean, right? So you take the sample mean and you subtract the population mean for each of your random variables, and you square that, and you multiply it by n, and you divide that by sigma squared, then that random variable, or that little manipulation, that has a chi-square distribution of 1. And the basic idea behind this proof is if you take xn bar, remember xn bar is normally distributed, if you subtract the mean and you divide by the standard deviation, which is sigma over root n, you're going to get something that looks like xn bar minus mu multiplied by square root n over sigma, which is a standard normal because xn bar is normal. And then if you square a standard normal, you're going to be left with the square root of n squared is just n, the square root of xn bar minus mu is xn bar minus mu squared, and the square root of sigma is sigma squared. So that's all that's saying. So I basically walked through that proof verbally. And then the last point is this one over here, which is if you take your each of your observations, subtract your mean and square that, and then divide by your sigma squared, or your population variance, and you sum all of those up, that will be a chi-squared with n degrees of freedom. And the way you prove that is, well, xi minus mu over sigma, that's because xi's are normally distributed, xi minus mu over sigma is just a standard normal, and then you're squaring that, so that's a standard normal squared, which is a chi-squared, and then you're summing those independent standard normals, so you're getting the chi-squared with n degrees of freedom, and I literally have a video about that. So yeah. Okay, now we can get to the proof. Now, the proof kind of is a bit weird because we don't really use MGFs. Well, we do use MGFs, but we don't do it in the same way. So basically, we can say that, well, it is MGF. So if we are proving that, using our setup that we had before, that n minus 1 s squared over sigma squared is chi-squared with n minus 1 degrees of freedom by the method of moment generating functions, right? This is equivalent to saying that the MGF of this whole thing, so the MGF of n minus 1 s squared over sigma squared of t is equal to the moment generating function for v, where v is some chi-squared with n minus 1 degrees of freedom. So that two statements and that two proofs are equivalent. So where the bulk of this proof comes from is proving that this is, or this particular moment generating function is that moment generating function. And we start off in a weird place. Well, we start off with the right-hand side first, usually. So the right-hand side is just mv of t, which is 1 minus 2t. That should be a 2. So that is a 2. Okay, so that's just showing what the right-hand side is equal to. The left-hand side, yeah, that's going to take some work. So we're going to define this other random variable, which seems like it's coming out of nowhere, but we're going to define w to be the sum from I is equal to 1 to n of the following: xi minus mu squared over sigma squared. Okay, so this is basically just taking all of the observations, subtracting the population mean, squaring that, and then dividing by our population variance, and then adding all of those up. So this, remember, is just a standard normal, right? And then you're squaring the standard normal and summing them all of these up, so we know that w is chi-squared, and that's one of our prerequisites. Here is where the proof gets to be interesting. So this is the same thing as the sum from I is equal to 1 to n. The bottom stays the same. Actually, I'm going to bring this sigma squared out because I don't want to write sigma squared every single time. But this is the same thing as saying xi minus xn bar plus xn bar minus mu all squared. So basically, we're adding something and then subtracting something, so we're adding 0, so we're not changing this. But what this allows us to do, I is equal to 1n, is then we can kind of put brackets here and use the square formula, or the binomial formula. So this is going to be equal to the xi minus xn bar squared, right? That's the first term, basically, plus 2 times xn bar minus mu. I'm going to write that first for a reason, we'll see later. And then xi minus xn bar, right, times by 2, because that's the product of the two inner terms. And then finally, we have plus xn bar minus mu all squared. Okay, so that's just the sum thing, where we've got one term plus 2 times another term, or we've got one term, another term, and a third term. Okay, so what we're going to do is we're going to separate the sum out, and we're going to divide by sigma squared for all of them, because remember, this 1 over sigma usually was at the bottom of the sum, and because it doesn't depend on I, we can bring it out, but now we're kind of bringing it back in. So this is going to be equal to I1 xi minus xn all squared, and then divided by sigma squared. And then we're going to add 2. So this I'm taking this 1 over sigma squared. I can bring it back in. I can leave it out. I can do whatever I want. It's a constant. So I'm going to leave it out here, and you'll see why in a moment. And then this sum, the sigma formula, the sum, is basically going to go in, and xn bar minus mu doesn't depend on I, so that's a constant, right? So I'm going to bring it out, xn bar minus mu, and then I'm going to have the sum, because xi definitely does depend on I, from I to n of xi minus xn bar, right? So that's what that sum is. That's the second term. And then the final term is going to be plus the sum from I is equal to 1 to n xn bar minus mu all squared over sigma squared. Okay, now where do we go from here? Well, the first thing we want to notice is this little thing over here. So this portion, this sum over here, is one of our prerequisites that we spoke about earlier, and it's this thing over here. When I take the sum of my observations and I subtract the mean off of that, and I sum through all of my observations, that's going to be equal to 0. So basically, what that means is that this whole thing is going to be equal to 0, but because I'm multiplying by something, it's going to mean that this whole term is equal to 0. So I'm just left with I is equal to 1 n xi minus xn bar all squared over sigma squared. Sorry, I'm writing quite fast. N xn bar minus mu squared over sigma squared. Okay, so that's what that is. Now, there's another thing that we need to notice, which is basically that in this term over here, right, this second term over here, I don't have any single, I don't have any single variable or I don't have anything in the sum that depends on I. So basically, this is just a constant being summed up n times, which means I'm just going to have n times that constant. So I'm going to have I xi minus xn bar all squared over sigma squared. And then I'm just going to have this constant value because this doesn't depend on I, and I'm going to be summing it up n times, so I'm going to have n times that constant value, x n bar minus mu sigma squared, mu all squared over sigma squared. Okay, so that's that. And then the final piece of the puzzle, or I don't know what part of the puzzle it is, but this little thing over here, remember that sigma squared we're dividing by it, we can just bring it out. So this is going to be 1 over sigma squared. Well, actually, no. I'm going to erase that because we do already have the prereq that we need. We don't need to manipulate it anymore. Sorry. Okay, so okay, so the second, or the whatever portion that we need to know, the next piece to the puzzle, is this little thing over here, this first term. Remember, we had our second fact, which is that basically this thing over here is equivalent to this thing over here. So what we can then write is this is equal to, oh, actually I don't need that either. I'm actually going to do just that. Okay, so this is equal to n minus 1 s squared over sigma squared plus n x n bar plus mu sigma squared over sigma squared. Okay, and remember that this is equal to w, which is what we had at the top, and remember what w was. Okay, so now what we're going to do is we're just going to define some new terms just so that we don't have to go about writing all of these horrible fractions. So we're going to let h equal n minus 1 s squared over sigma squared, and we're going to let u squared equal n x n bar minus mu squared over sigma squared. And the reason I say u squared is because this whole term over here is just some normal distribution, some standard normal random variable squared. And the reason we know that that's a standard normal squared is because of this fact over here, basically. Okay, so now we have that, and remember, we know that u squared is a chi-squared with 1 degree of freedom. Okay, so we have that w is equal to h plus u squared. Now, remember that we know that, I don't know if I can, yeah, still got space. Okay, so we know that w is a chi-squared with n degrees of freedom, and we know that u squared is a chi-squared with 1 degree of freedom. So if we take the moment generating function, right, of w of t, but using this formula, right, we know that it's going to be equal to the, this is basically going to be equal to e of etw, which we can use the actual definition that we have for w that we've manipulated basically to be e to the t of h plus u squared. And then when we bring that out, it's going to be e to the h plus tu squared, which is e of e to the th multiplied by e to the tu squared. And now this is important because we've got this function of u and we've got this function of h. Now remember that h is equal to n minus 1 s squared over sigma squared. So h is a function of our sample variance, and mu, not mu, u squared is, well, our definition of u squared is nxn bar minus mu squared all over sigma squared. So u squared is a function of xn bar. So we have a function of our sample variance and a function of our xn bar, which is our sample mean. And based on this fact over here, that our xn bar and our sample variance are independent, it means that any function of those two things are independent. So that means that h and u squared are going to be independent, which means if I take any function of h and u squared, those are going to be independent. So I can separate this expectation out, right, multiplied by e of e to the tu squared. But this over here is just equal to the moment generating function of h of t multiplied by the moment generating function of u squared of t. Okay, so now we have this result. I'm just going to bring us back up here to the home stretch. So I'll just write out what we have. We have that the moment generating function of w is the moment generating function of u squared of t multiplied by the moment generating function of h squared of t. And we also know that w is chi squared of n and u squared is chi squared of 1, which means that the moment generating function of w should be equal to 1 minus 2t to the power of minus n over 2, and the moment generating function of u squared should be equal to 1 minus 2t to the power of minus a half. So then using these two facts and this fact over here, we can write that the moment generating function of h of t is equal to the moment generating function of w divided by the moment generating function of u squared of t, which is 1 minus 2t to the power of minus n over 2 over 1 minus 2t to the power of minus 1 over 2. So those are the same base. We can add the exponents. So that's 1 minus 2t to the power of minus n over 2 plus 1 over 2. But that's just equal to 1 minus 2t to the power of minus n minus 1 over 2. And that is equal to our right-hand side. If we look at what our right-hand side was, right? Sorry, this should be n minus 1 over there, because remember v is chi squared with n minus 1. So that's 1 minus 2t to the power of negative n minus 1 over 2. Sorry, so our right-hand side should have been n minus 1 over 2. So that right-hand side is equal to our left-hand side, which is, remember our left-hand side is the moment generating function of h, which, well, h is this thing over here, n minus 1 s squared over sigma squared, but we said that s squared, n minus 1 s squared over sigma squared is what we were trying to prove. So because we proved that m of h of t is equal to mv of t, we have therefore proven that n minus 1 s squared over sigma squared is a chi-square distribution with n minus 1 degrees of freedom. Okay, wow, that was a lot of work for something that is rather mundane, but regardless of that, it's still something that could possibly get asked in an exam. Whether they do it, I'm not sure, but regardless of that, you now do have the proof, and I will also have the PDF of all of the proofs that I have videos for so far down in the description below. So yeah, cool beans. Like and subscribe and comment if you have questions or requests or anything like that. And yeah, that's it for me. Cool beans. Bye.